Strong induction as a process looks similar to what we have with mathematical induction, but there's one big and massive leap that you actually already saw in the ladder that I displayed before, but a couple things here. Number one, there is a couple of different names that we can have for strong induction, second principle of mathematical induction or complete induction, so just heads up if you happen to be looking at other resources. You're going to prove that P of n is true for all positive integers of n, and 0 is not a positive number. It is an integer, but it's not a positive number, as I'm sure you know already. Where P of n is a propositional function, there's going to be two steps. These look familiar. We have a base case. We're going to verify the position of P1 is true. But here's the inductive step, and that's where things go completely different. Remember we did P of k and then k plus 1? Well, here's the interesting part. Here's the building of that ladder that it worked for P1 and P2 and P. By the way, I put this highlighted bold thing in there because that's going to show up in your homework. Because remember, it's going to go all up to pk. Okay, that's, remember, what we used. Pk is what we used in our mathematical induction. We're going all the way up there. K minus 1 is going to be just before that k, and that k minus 1 helps us actually change starting positions once in a while, so that's why I put that there. But we're still going to assume that it helps out with our pk plus 1 for all positive integers of k. So we're assuming this whole gigantic ladder that you and I have stepped up and done is completely true, and now we're going to try to do that for k plus 1. Now again, it's called strong because you're assuming much more in your hypothesis, and you've probably done, you'll see some examples where we've done a lot of these P2, P3, P4 in a certain examples that we've had here. So in your overall structure for this, these are almost duplicated, but still, you can reach the first rung of the ladder with our base case. Then in our induction step, we're going to assume a lot when it comes from starting from P1 and P2. By the way, this can shift just slightly too. Maybe it has to be P2, but again, we're starting at the bottommost rung that we're given a range for, and then going all the way up to PK, and then we try to PK plus 1. And we're going to show that PK plus 1 must also hold, and again, that's a big difference from our mathematical induction. I think it's time to show you an example. This is not using strong induction yet. This is using mathematical induction. So this should look really familiar. And by the way, it's using mathematical induction with cases too. In the example I'm showing you here, I actually expanded a little bit more than what you see in the book. The book is, I'm going to show you the exact same problem done in strong induction here in a moment. So we want to compare between the two of them here, which we'll do here in a second. If we're using regular mathematical induction, all this should look pretty familiar. Our P of n is going to be postage cent of n cents, can be formed by using 4 and 5 cent stamps. 4 and 5 cents, but anyway. The base case is postage of 12 cents can be formed using 3 4-cent stamps. By the way, notice we don't have a P is 12. P of n, or sorry, n is 12 on this one. It's not 1. So there's already, notice that shift that we have. Now, we're okay with mathematical induction to do that. Okay, there's no problem. But we can also do the same thing in strong as well. So just heads up on that. We go ahead and prove it being true. I don't need any combinations of 5-cent stamps. I just need 3 4-cent stamps to get my true. The base case is good. So now I'm going to try for PK for any position, positive integer k, that is postage of k cents, can be formed using combination of 4 and 5 cent stamps. So I must show that PK plus 1, where k is greater than 12, we consider two different cases on this one. Case 1 is that at least one 4-cent stamp has been used, then a 4-cent stamp can be replaced with a 5-cent stamp, to yield a total of k plus 1. Okay, so there's my one part. Now, as you can see, I kind of laid this all out. There's my original was 16, which is greater than 12. I went to 17 to do that k plus 1. All I had to do was replace one of my 4-cent stamps, add a 5-cent stamp, and bam, there is my k plus 1 using that case. For case number 2, and I am tongue-tied as all get out, so bear with me here. Otherwise, a 4-cent stamp has not been used, and at least 3 5 were used. Now, why 3 5? 3 5-cent stamps, because again, they got to be greater than 12. Okay. The 3 5-cent stamps can be replaced by 4 4-cent stamps to yield a total of K plus 1. Whew, I got through that. You know how many takes I actually took to do that. But anyway, again, I'm just showing examples. Here's 15, where I had 3-cent stamps. 3 times 5-cent stamps. I replaced all those 5 with now 4 4-cent stamps to make my 16. There's my making of a K plus 1. And then again, the same thing down here for the bottom, where I had 25-cent stamps. I can still replace that. I still have 2 left, but I can add them with 4 more 4-cent stamps to make 26. So notice I did this one by cases for this particular mathematical induction, and that worked out. Okay. Now, that's fine. There's nothing wrong with what we did here. I don't want you to think that you can't suddenly use a proof, a mathematical induction proof for a problem like this. But we're just showing you an alternative, which we're going to do next. This one's interesting because of 2 things. Number 1, I have to start at 12. Number 2, in my let P of n, matter of fact, I should take the let out of there, but anyway, same thing. But notice my base cases on this one. On my base cases, I went ahead and did P of 12, P of 13, P of 14, P of 15. Notice there's my rungs on the ladder going up. That's really my P of, not 1, but P of 12 and P of 13 and P of 14. I'm going to assume that it's going to hold for all that, where now my next value above that's going to be 16. So I must show that P of k plus 1 is true, but I'm going to do something sneaky. I'm going to do that pk minus 3 because of my 4-cent stamp item. So I've stepped up 4, but I'm going to go back 3 here to try to get it to the next one up. So I kind of cheated on this one and reread that one, so we're okay with this. But the P of k minus 3 holds because k minus 3 is still greater than 12. And it just repeats itself, as you know, after that 4th step. So just remember that the k minus 3 helped us to get to that k plus 1 using the incrementation of the lowest postage cost of 4. Hence, P of n is going to hold for n greater than 12. Here's example number 2. And yeah, it's different. We're going back into primes and product of primes and composites. So remember a couple of pages earlier about those terms? Make sure you kind of looked over for a moment. So my base case, and again, this integer is greater than 1, okay? Then n is prime or product of primes. Base case, we notice we start off at 2 because it's got to be greater than 1. So 2 times 1, that is prime, so that's going to end up being true. So we're good with that. Inductive hypothesis, k is an integer greater than 1. K is a prime or a product of primes. And I got to show that it's going to work with P2, P3, P4, all the way up to pk minus 1, up to pk to see if pk plus 1 will hold an arbitrary value integer k. So here's a proof. We're going to use a direct proof. It's been a while since we've looked at a direct proof on this one to assume that all of these are true. Now, a direct proof is really back in the terms that you and I just talked about. If k plus 1 is prime, then p of k plus 1 is true, because again, we're trying to see if it is prime or not. Or it's either a prime or composite. So a composite, k plus 1 is a composite, can be written as a product of 2 positive integers with a of b, and then you have your 2, notice that the 2 comes up, is less than or equal to a, is less than or equal to b, is less than or k plus 1. So with k plus 1 being larger than everybody else, it can be then broken down into smaller composites, which was all of these items that you and I just tried before that. That's going to be smaller than k plus 1, and we've just already proved that that part's going to be, well, we've assumed that part's going to be true. So that's where we can get away with that P2, P3, all of those items we would have gotten up to this part because it's either a prime or a composite, and it's going to be less than pk plus 1, which we know is going to be true. So, and again, this is what it would look like if you and I were to write it out. These are all just a further breakdown of what 24 would be. So by the inductive hypothesis of A and B, they can be written as a product of primes, and you can read the rest of that on your own there. But that is another breakdown. And notice again, I use a directed proof on this to kind of make things help work us out here. But again, notice I'm assuming all of these work before I got to the k plus 1. That's the big deal when it comes to this. And we should be able to with the overall definitions we were given in this particular example.